Welcome back everyone. In the last few lectures we have seen different types of specifications for a system. In particular for second order systems, standard second order systems, we had found that the specifications are percentage overshoot, settling time, rise time and peak time. We had also seen that in general there can be another specification which is called the steady state error of a system, and we also studied the idea of type of a system which is linked to steady state error of a system. Today we are starting something new which will be very important for us while designing controllers, and that is called root locus. What is root locus? How is it useful? We will come to that, but before that let us try to understand how do we evaluate a transfer function at a point on the complex plane. Remember, transfer functions are nothing but rational functions where the numerator is a polynomial, the denominator is a polynomial. So, I can always evaluate that rational function at different points on the complex plane. So, basically I replace the value of s with the complex number and I get a new complex number. That is what transfer functions are. Transfer functions can be evaluated at a particular point on the complex plane. So, let us say we have a polynomial of this form s plus 2. This is not even a transfer function, this is a polynomial. Okay. So, s plus 2 I want to evaluate it at 3 plus 4j. So, how do I evaluate this at 3 plus 4j? One way is simply just put in place of s equal to 3 plus 4j and then you will have this value. So, it will be 5 plus 4j. So, it will have a magnitude and an angle as well. Now, instead of this we can do the same thing using graph or plots as well. So, this is how we can do this. So, s plus 2, if you think of it as a transfer function, it has a 0 at minus 2, right, or the root of the numerator in this case is minus 2. So, this is your 0 say. So, this is the complex plane, and I want to evaluate this function at 3 plus 4j, suppose this is that 3 plus 4j point. So, this value that you are getting where you have a magnitude and angle is nothing but if you draw a vector from the point minus 2 to 3 plus 4j, the magnitude of this vector will be root over of 5 square plus 4 square, and the angle here will be tan inverse of 4 by 5. Notice that this is 5 and this is 4. So, diagrammatically also we can directly find out what is the evaluation of this polynomial at the point 3 plus 4j. Similarly, we can also ask what is the evaluation of this transfer function say. Okay. So, what is the evaluation of this transfer function at the point 1 plus j? So, one way is that you just plug in the value of 1 plus j there and it is done, but we will try to do it pictorially. So, in this case there are two zeros at minus 4. So, these are the two zeros, and there is a pole at minus 2, this is a minus 2, okay, and we want to evaluate this transfer function at this point. Okay. Do not consider this to be coming out of a physical system, because you see the numerator here has a degree higher than the denominator, which means this is a non-causal system, and in this class we are not talking about non-causal system. Just think of it as a mathematical object now. Okay. It has nothing to do with physical system. Suppose you had a mathematical function which is a rational function, there is a numerator and a denominator polynomial, and you want to evaluate it 1 plus j. This is how you can do this. Now, the evaluation can be done in this way. So, from these two zeros there will be two lines going m1, and there will be two lines going m1 and another line will be m3, and from the pole here, this is a minus 2, right, the pole is here, m2 will be going. So, in that case the evaluation of this would be, since there are two zeros here, so corresponding to that, and it is in the numerator, the magnitude for this will be m1 into m1, and since the pole is in the denominator, the magnitude is in this case is from the pole is m2, okay, to this location 1 plus j. So, this is m1 into m1 by m2. And about the angles as well, since in the numerator we have the zeros, the angle phi 1 here is phi 1 plus phi 1, because there are two zeros here. So, we will have angle phi 1 plus phi 1, and since in the denominator we have the pole, so this phi 2 will be subtracted now, okay, and this is how you can evaluate this rational function at the point 1 plus j. You can go ahead, do the calculations, it is straightforward. Once you do the calculations, these are the values that you will get, because this is 5, right, and this is 3, the magnitude. So, this way you can find out, and finally, the expression will come out to be this. You can check, this is the expression we got pictorially, just plug in these values at this point and try to evaluate this function, then you will see that you will get the same values. Why are we talking about all this? We are talking about all this because we will try to see how does it link to the poles of a closed loop system. Okay. So, you know what evaluation is, how we can evaluate. Now, let us go back to a standard feedback configuration of this form, where we have a controller, we have a plant, and we have a feedback transfer function as well. So, if I have to find out the closed loop transfer function, the closed loop transfer function will be C by R, in this case is kg by 1 plus kgh. Now, if I ask you what are the poles of this system or what are the closed loop poles of this system, okay, then the meaning of this is, if this is the transfer function which is this, what are the poles of this system? Okay, that is the question that we are asking. Now, we know that in order to find out the poles of the system, the closed loop poles must satisfy 1 plus kgh hs. Think of it in this way. So, this is your complex plane, right, this is your complex plane. So, what are the points in this plane that satisfies this equation? Those points in this plane that satisfies this equation are the closed loop poles of the system. I hope you understand that. So, we will try to see how does this information help us. You see, finding out solution of this system is equivalent to finding out solution of these equations, kgh equal to minus 1. Now, look at it from the perspective of magnitude and phase. So, what does this mean? See, you can think of this as the fs transfer function that we took in the last example. The question that we are asking is, what are the values of s that I can put here so that I get minus 1? And minus 1 can be written as magnitude 1 and angle 2k plus 1 into 180 degree, right, if I write it in magnitude and phase form or angle form. So, basically the question that we are asking is, what are the points we should put here that will result in magnitude 1 and phase angle of odd multiple of 180 degree. This is called magnitude criteria and this is called angle criteria. So, all the points on the complex plane, that satisfies both the magnitude and the angle criteria are the points which will become closed loop poles of the system. Okay. So, that means in other words, you can find out a value of k by which you can place the poles at those points. Notice this angle criteria carefully. In this angle criteria, there are 3 terms k, gh and hs. K is a constant term, right? We had discussed this, we had already taken k to be a constant term. Now, what is the angle contribution from a constant term? It is tan inverse of 0 by k, right? And what is tan inverse of 0? We know that it will come out to be 0 degree, right? So, the angle contribution because of k is, there is no angle contribution as such, right? So, the only angle contribution is from g and h. So, k I can remove from here because k is not even dependent on s, right? So, it has no angle contribution, correct. So, I can actually go ahead and remove this k. So, this will be the magnitude criteria and this becomes your angle criteria, where you see in the angle criteria there is no mention of this capital K, which means that if someone asks me if this point is a closed loop pole, can it be a closed loop pole? So, what I have to do is I have to check the angle criteria first, and if it satisfies the angle criteria, then I have to go here and find out the value of K. We will take an example and see that. Here is an example, okay. Suppose your transfer function, Gs transfer function is 1 by s plus 4, okay. So, I should not have written here, suppose G1 in this case. So, this is G1, okay. So, these two together Kgs is equal to G1s and Hs in this case is 1, it is given to us, okay. So, the question being asked is minus 3 plus 2j a closed loop pole? So, see, if minus 3 plus 2j has to be a closed loop pole, it has to satisfy both this criteria, right? We have seen that. Satisfying both this criteria is equivalent to saying that this equation is satisfied at the point minus 3 plus 2j. That means, you can find out a value of k such that this equation is satisfied. Okay, so let us check whether this is satisfied or not. So first we will check the angle criteria. So we have to find out angle, right? So what do you mean by checking the angle criteria? So I will find out, evaluate GS into HS at the point minus 3 plus 2j, right? That is why we were discussing evaluation to start off with. I will evaluate these transfer function GS into HS at the point minus 3 plus 2j and check what is the angle part. I am not concerned about the magnitude part yet. I am just concerned about the angle part first. Okay, so we'll just check what the angles are. So how do I evaluate? We know the pictorial way, right? So let us try to do that. So minus 3 plus 2j is this point. This is the point where we want to evaluate the angle. How many poles does it have? It has one pole at 0 and one pole at minus 4. So okay, this should have been a pole. This should have been a pole. Okay, so there is a one pole at 0 and one pole at minus 4. So what are the angles that are coming in? So since and there is no 0, right? There is no 0 at the top, so forget about the 0. So what will be the final angle contribution? The final angle contribution will be minus phi 1 minus phi 2, right? Why? Because you see these are poles only. So it will become negative because it is in the denominator. When it goes up, it will become negative. So now let us look at the angles. What are the angles here? So you see, again this is a pole here. So what are the angles? So the angle phi 2 in this case is 180 degree minus this angle. And what is 180 degree minus this angle? This is tan inverse of 2 by 3, right? So 180 degree minus tan inverse of 2 by 3, this is phi 2. And what is phi 1 in this case? Phi 1 is tan inverse of 2 by 1. This is 1, this is 2. So this, and both are negative. So this is phi 1. So minus phi 2 minus phi 1. Does it come out to be 180 degree? No, it does not come out to be any odd multiple of 180 degree. So if it is not an odd multiple of 180 degree, that means I can directly say that there is no way that I can find out a value of k that will satisfy both these conditions. Even if one of these condition is not satisfied, then we are done. But I mean, notice actually we do not even have to satisfy one of these conditions. I just have to check whether the angle criteria is satisfied. Because if the angle criteria is satisfied, I can always find out a value of k. Suppose I find out a s which satisfies the angle criteria. So then I just go here and plug in the value of s. I calculate this k, I can find by 1 by mod of GH HS at that point, right? So first thing that we should check is angle criteria. That's why many students I have seen over the year makes a mistake of finding out checking the magnitude criteria first. But no, magnitude criteria is satisfied by every point on the complex plane. You take any point, you just plug it in there, you can find out a value of k, right? So magnitude criteria is satisfied by all points. What is important is the angle criteria. Angle criteria is not satisfied by all points. So you have to plug in and check whether the angle criteria is satisfied. If it is satisfied, then you can always find out the value of k. Okay. So in this case, it is not satisfied. Let us take another example. Is minus 2 a closed loop pole? Same question, minus 2 a closed loop pole. Again, this is a pole here. Okay. So if minus 2 is a closed loop pole, I am asking. So this is at minus 2. So what I will do? I will draw two lines towards this, right, and check what are the angles. So when I draw this, you see the angle made by this, let me call it a phasor. So the angle made by this phasor is 180 degree, right? And the angle made by this phasor is 0 degree. So what is the total angle? Minus phi 2 minus phi 1 is minus 180 degree, which is an odd multiple of 180 degree, right? So which means that minus 2 is indeed a closed loop pole. So that means I can find out a value of k for which minus 2 will be a closed loop pole. So now you see I use the magnitude criteria to find out that value. So at s equal to minus 2, I evaluate this. So k will be 1 by GS HS at s equal to minus 2. Okay, and this comes up to be 4. This means that if you put k equal to 4 here, then this system will have minus 2 as one of its poles. Okay, so you can check that quickly. So if it is 4, what was the transfer function of this system? The transfer function of this system was kg by 1 plus kgh, the closed loop transfer function. So that becomes k by s into s plus 4 by 1 plus k by s into s plus 4. So this is kgs, it's correctly written. So now you have k is 4, right? So this is 4 by s square plus 4s plus 4. So you see s square plus 4s plus 4 is s plus 2 whole square. So minus 2 is indeed a pole of the system. Here is my question, is minus 1 a pole, closed loop pole of the system? So minus 1 will be somewhere around here, right? Yes, minus 1 is also a closed loop pole, because you see again the angle criteria is satisfied. You can go ahead and find out the value of k again. So, this is an exercise for you. Find out the value of k when minus 1 will become a closed loop pole, and try to check what are the poles that you are getting. Try to do the same thing. You will see at least one of the closed loop poles will turn out to be minus 1. The second one might not be minus 1, it might be something else, but at least one of the poles will turn out to be minus 1. So, what is root locus? This is the point where we started this entire lecture with, right? What is root locus? Root locus is nothing but the collection of all the complex points, complex numbers on the complex plane which will qualify as closed loop poles of the system when k is varied from 0 to infinity. So, if I vary k from 0 to infinity, typically, although k can be varied from the negative side also, for now let us assume that k is varied from 0 to infinity, k is a positive number. So, when k is varied from 0 to infinity, you will get different pole locations, closed loop pole locations, because you see in the previous example itself, the transfer function came out to be, so s plus 4 by 1 plus k by s plus 4. So, the closed loop transfer function is this. So, now as I vary the value of k, the location of the pole locations will change, closed loop pole locations will change. So, the collection of all those points is the root locus for this system as k is varied from 0 to infinity. And by now you also understand the points that I will get must satisfy, all those closed loop poles must satisfy the angle criteria and the magnitude criteria. It has to. Then only it will become a closed loop pole. There is no other way, because these two criteria came from this equation, right. So, these two criteria are equivalent to the points which satisfies these two criteria is equivalent to satisfying this equation 1 plus kgh hs gs hs equal to 0, which is nothing but the closed loop poles of the system. And you should also understand now that when I say root locus, it is a plot, right, and it is a plot on the complex plane. In this complex plane, it will be a plot where I will collect all the closed loop poles and then I will try to plot it. That is what root locus is all about. And root locus will become a very important tool for us when we design the controllers. In the next lecture, we will look into the rules by which we can design these root locus. Instead of each and every time changing the value of k and finding out closed loop pole locations, we will come up with some rules by which we can directly draw the root locus, and then we will proceed from that point to controller design. Thank you.